packed in there very closely. They have a strong attraction to each other. Lots of strong intermolecular forces. Now, if you're going to a liquid, you're going to break some of those, but a lot of those intermolecular forces are still there because the particles are still very close together. Now, they're freely moving. They can tumble and move all over each other, but there's still a lot of intermolecular forces present. So you're only breaking a small fraction of the intermolecular forces. Whereas if you're going from a liquid to a gas, you're taking lots of intermolecular forces and you're completely breaking all of them. So it's going to require more energy to break all of those intermolecular forces, hence the larger amount of heat for the heat of vaporization. Okay, and you would use this heat of vaporization the exact same way that I just used the heat of fusion. Okay, so let's do an example for a calculation that has multiple steps. Okay, because this is really where it gets useful. You can do individual step calculations, but it gets harder when we put it all together. And by putting it all together, I mean this. Let's say we have 125 grams of water that originally is sitting at negative 6.0 degrees Celsius, but we want to get that up to 12.0 degrees Celsius. Okay? Now, what are we doing to the temperature? We're increasing it. So is that going to require heat or release heat? Good. It's going to require heat because we are increasing the temperature. So now what I want you to think about is, all right, this water is starting at negative 6 degrees Celsius. What state is it starting at? If it's at negative 6 degrees, hopefully you realize that's below its freezing point, right? So the first thing we're going to have to do is, in order to get it up to 12 degrees, the first thing we have to do is increase the temperature of our solid up to the melting point, okay? Which, you know, the melting point of water is at 0. So what we have to do is heat the solid from negative 6.0 degrees Celsius all the way up to 0 degrees Celsius. Okay, that's the first step that we're going to have to do. The second step, now if you can think about what's occurring, we are at 0 degrees Celsius after this first step, and what we're going to have to do is a phase change. We are going to have to do the solid to liquid phase change as our second step, right? Because we're already at 0 degrees Celsius, that's where it melts, so we actually have to give it enough energy to do that melting process. And then the third step, if you see, because now we're going to be a liquid, but we're a liquid at 0 degrees Celsius. So now, in order to get up to 12 degrees Celsius, we are going to have to do one more step where we heat our liquid from 0 degrees Celsius all the way up to 12.0 degrees Celsius. Okay, so just to take 125 grams of water from negative 6 degrees all the way up to 12 degrees Celsius, just to do that little process, we're actually going through 3 independent processes. Okay, and so you're going to do those calculations for those independent processes independently. So let's do that. Let's say the first step is just heating the solid from negative 6 degrees Celsius all the way up to 0. Now, if we are heating a solid, it is staying in the same state. It's still going to be a solid. So what are we going to use in order to calculate how much heat is required to do this? Q equals M times C times delta T. Okay, so Q equals M, our mass is 125 grams. Our C, now C is going to be a little different because each state actually has its own heat capacity. The heat capacity for solid ice, I'm just gonna approximate it. It's about 2 joules per gram degree Celsius. It's a little over that, but we'll just use 2 for the sake of simplicity. You guys have, I'm sure, used the liquid water heat capacity. That's the 4.184 joules per gram degree Celsius. But for a solid, it is different, so I'm going to use the different one. And then what's our delta T going to be for this process of heating solid? We're going from -6 all the way up to 0, and so that's just going to be a change of 6.0 degrees Celsius. So if you plug that in, you should get 1,500 joules. Okay. Technically, well, we have 2 sig figs in our temperature, so let's just keep 2 sig figs for our answer of 1,500 joules. So that would be the amount of energy required to do process 1, heating our solid, 1,500 joules. So I'm going to keep a little tally over here. So heat solid, we got 1,500 joules. And then we're going to go on to the second process. So now we have to go from solid to liquid. Okay, in order to do that, don't forget we're going to use our delta H of fusion, which is 6.02 kilojoules per mole. Okay, so all we need to do in order to figure out the amount of energy required to do this phase transition is we're going to multiply it by the amount of moles of water that we have. So 125 grams. Again, we'll just divide by the molar mass to get moles. And so 125 grams by 18, we have a 6.94 moles of water. So we'll take this molar heat of fusion, multiply it by 6.94 moles. If you notice here, the moles cancels. We're left with just kilojoules, which is what we want, or at least joules in general. So 6.02 times 6.94, and we get, 6.02 times, we get 41.8 kilojoules. Okay, so over here in our little tally, going from solid to liquid, we will use 41.8 kilojoules, but let's keep all of the units constant or consistent here. So I'm going to change the 1,500 joules to 1.5 kilojoules. That's just moving the decimal over 3 spots. And then I can keep this as 41.8 kilojoules. Notice it takes a lot more energy to do the phase changes because you're actually breaking intermolecular forces. In this heating of our solid, all we were doing was just increasing the velocity of the movement of the particles. Okay, so that is the second step. And then the third step, where we heat our liquid. Again, now it's just heating the same state. Okay, we're just a liquid. It's not changing states. So when we're heating the same state, all we're going to use is Q equals M times C times delta T. So we will still have 125 grams. Now it's a liquid, so we can use the heat capacity, 4.184 joules per gram degree Celsius value, because that's associated with liquid water. And we're trying to get it up in temperature from 0 to 12 degrees Celsius. So our delta T will simply be 12.0 degrees Celsius. And so we'll have 125 grams times 4.184 times 12 degrees. And we get a Q value of 6276 joules let's make that 3 sig figs and turn it to kilojoules. So that's going to be 6.28 kilojoules. Okay, so over here, heat our liquid, it took 6.28 kilojoules. Turn on some lights, it's getting a little dark. I hear kids playing outside. How dare they have fun? Okay, anyway. Okay, so let's take this information and let's make our own phase diagram, because that is what you guys will have to do for your assignment. So again, we have temp in degrees Celsius on the y, and then heat added in, let's do kilojoules on the x-axis, okay? Now, we started this process at -6 degrees Celsius, so I'm just gonna put that randomly. It doesn't really matter where you start it, but since we're going up in temperature, I'm gonna put that near the bottom, and that was the temperature that our 125 grams of water was poised at before we added any heat. Okay, so this would be 0 heat added. We are at a solid at -6 degrees. Now, if we add 1.5 kilojoules of energy, okay, well, I'm just putting the 1.5 on the axis here, we would get up to 0 degrees Celsius. So we would go from that point up to this point, and we can connect those two dots, okay? So after 1.5 kilojoules of heat is added, we increase the temperature from -6 degrees all the way up to its melting point. Now remember, when it's going through this phase transition, the temperature is not changing, okay? So even though we are going to use 41.8 kilojoules throughout this entire melting process, we are not going to, it's a terrible line, but we're not going to change the temperature. So it's just gonna stay constant, okay? But here on the x-axis, we're gonna keep track of the total amount of heat added. We already added 1.5 kilojoules of energy to do the heating of the solid. Now we're adding another 41.8 kilojoules for a grand total of 43.3 kilojoules. Okay, this is just kind of a running tally of the total amount of energy that we've used. So at 43.3 kilojoules of heat added, we've done the heating of the solid, heat solid, and then we've also done the solid to liquid phase transition. Now we just have the third step when we add another 6.28 kilojoules, we would get to a total of 49.6-ish kilojoules, and that would get us up to 12 degrees Celsius. So let me put that point. Okay, and this would be where we are heating our liquid. So here's a phase change diagram for the process of taking 125 grams of water from -6 degrees Celsius all the way up to 12 degrees Celsius. The grand total of energy required to do this is just the sum of the three at 49.6 kilojoules. All right, part 1 complete.